In today's lecture, we'll talk about transient conduction or unsteady state conduction. Before going to what is transient conduction, first let us see the conduction. Conduction is a mode of heat transfer that occur in all the three states of matter which are at rest. The energy transfer takes place due to lattice vibration and the presence of free electrons. The conduction can be broadly classified into steady state and unsteady state conduction. In steady state, the temperature does not depend on time, or it does not vary with respect to time. But in the case of unsteady, the temperature is a function of spatial coordinates as well as time. So in the case of steady state conduction, we can write the temperature as a function of x, y and z, or the spatial coordinates in Cartesian coordinate system. But for unsteady, it is not just the spatial coordinates, it is also a function of time, tau. Here I am using the notation tau for time. The small t which we had used earlier for time, we are using it for some other purpose in this transient conduction. So I am not using small t here. Instead of that, I am using tau for time. Now let us go back to the history and see when the importance of transient conduction or transient heat transfer was realized. In 1712, that was the beginning of the Industrial Revolution. The use of engines in the industries were at the beginning stages, and Newcomen's steam engine was one of the oldest steam engine, which was used to pump water from mines. So as the miners dig up, the water used to accumulate in the trenches of the mine, that has to be removed, that has to be lifted up. So to run the pump, they used these steam engines. The drawback with this engine is that the condensation of the steam used to occur inside the engine cylinder. So when the condensation is occurring, that occurs after the expansion of the steam. So there will be special devices which injects water into the cylinder after the expansion of steam. So the water absorbs heat from the steam and condenses the steam back to liquid state. When the water gets back to liquid state, it produces a vacuum, because liquid water occupies very less space when compared to steam. So that produces a vacuum and that pulls back the piston, so providing additional amount of energy. But the drawback here is the engine is slow, because it takes a lot of time to condense and then pull back the cylinder and remove water from the engine and then add steam to it. And also this engine cylinder is going through a cyclic changes in temperature. So during a power stroke or the expansion, the temperature of this cylinder increases, and during the next stroke, the temperature of the cylinder reduces. So that also reduces the thermal efficiency of the engine. So the amount of energy output from the engine will be very less. So in 1977, James Watt was called on to renovate the engine, or to modify the engine to provide a better efficiency. So what he did is he studied the engine and he realized by providing an external condenser instead of condensing the steam inside the engine cylinder, he can eliminate the cyclic changes in the temperature and the engine cylinder can operate at optimum temperature. That increased the efficiency 100%. So initially Newcomen's engine was 1.1% efficient. Now that has been increased to 2.2. Although these number are very small when compared to modern day steam engines, the increase in the efficiency was very high at that time period. So the Watt showed that by eliminating the transient heat transfer, the efficiency of the engine was increased, and that gave us the importance of transient heat transfer that should be considered while designing any component or any heat engine. Now let us see a few examples where the transient heat transfer comes into picture in our day-to-day life. The first one is the body temperature measurement. So if we want to measure the body temperature, then what we do is we use thermometer. So we use thermometer, we keep the thermometer in our mouth for around 30 seconds to 1 minute, and then we will be able to measure the temperature of our body. That is because initially the thermometer will be at room temperature, and when it comes in contact with our body is at a higher temperature than the surrounding room temperature. So it will take certain amount of time to reach that temperature. Once it comes in thermal equilibrium with our body, then we will be able to measure our body temperature. So there is a change in temperature with respect to time, that is unsteady conduction, or you can call it as transient heat transfer. So that is one of the example. The second example is the periodic heating and cooling of earth surface as well as the buildings. During daytime we receive a lot of energy from the sun, and that increases the temperature of the surface of the earth as well as the buildings. And during night time, as the temperature reduces, as there is no sun which is providing heat energy, the temperature of the body keeps on reduces, and that happens on a regular basis, or over a period of 24 hours there will be increase in the temperature and reduction in the temperature. Similarly, cooling of the IC engine. IC engines has to be cooled because during power stroke or during combustion a lot of energy will be released, and for optimum working condition we need to reduce the temperature of the cylinder to maintain a proper film lubrication film inside the cylinder, and to avoid knocking and all, we need to make the engine, or we need to keep the engine at an optimum temperature. For that purpose, again here the temperature of the cylinder will be increasing and reducing throughout a cycle. So that is another example of transient heat transfer. Then heat treatment of engineering materials. So to provide proper hardness or to provide the desired quantity, the properties, what we have to do is we need to heat the metal and then we need to bring it back to a certain temperature. For that, generally we quench the engineering materials in oils, and there when we quench the material in the oil, the material temperature goes to a very low temperature from a very high temperature within a short duration of time. That is another example of transient heat transfer. Now let us see the different types of transient heat transfer. As I have given the examples, heating and cooling of IC engines as well as heating and cooling of earth and buildings, these occurs on a regular periodic basis. So these are called periodic transient conduction, where the temperature changes are periodic in nature. So they happen over a period of time. Repeatedly there will be increase and reduction in the temperature over a period of time. But the example of heat treating of engineering materials or metals, or the burning of bricks, the red bricks has to be burnt before they will be useful for building construction, and cooking. So we need to heat the grains to cook them. So all these there will be changes in temperature with respect to time, but they are not periodic in nature. They happen once or they may happen twice, but they are not on a regular basis. They are called non-periodic transient conduction, and here the temperature varies non-linearly with time. Then let us see the methods of solving transient conduction. There are basically four methods: analytical method, graphical method, analogical method, as well as numerical method. But in our syllabus we are restricted to analytical as well as graphical methods of solving the transient conduction problems. Now let us see an analytical method. So the first method which we are going to study is lump system analysis. Here The condition is that the transient heat conduction in solids with negligible internal conduction resistance compared to convective resistance at the surface. So here we are dealing with conduction within the body and convection from the body to the surrounding fluid. For example, if you are heat treating a material, then you will take the hot workpiece and quench it in oil. So when you are quenching it in oil, so the material is surrounded by the oil, which is a fluid, and convection happens between the surface of the solid and the fluid, the oil, and there will be conduction within the material. So now we are dealing with the internal conduction resistance and the convective resistance at the surface. So if the conduction resistance within the body is very less when compared to convective resistance at the surface, then those kind of cases can be called as lumped system analysis. It means to say that whatever may be the shape or geometry of the object, we are considering that as a lump of mass or a point mass, and then we are analyzing that. So that simplifies our calculation. The major thing which we need to remember here is if the internal conduction resistance is less than the convective resistance, which means to say that the temperature within the body will remain almost whatever may be the position, it remains same within the body. There will be no variation of temperature with respect to spatial coordinates within the body. So those kind of cases we call it as lumped system analysis. So later in the next lecture we will see the criteria on which we decide whether we can apply a lumped system analysis or not for a given transient conduction problem. Now the examples are heat treatment of small components, measurement of temperature with thermocouple or thermometer are some of the examples for lumped system analysis. Now let us see how to derive at the temperature distribution equation in the case of lumped system analysis. For that I am considering a solid body which is having a mass of m and then volume v, density rho, and temperature Ti. It has a surface area of Ta, surface area A, and that is surrounded by a fluid. It is surrounded by a fluid which is having a heat transfer coefficient of H and temperature Ta. One of the assumption is that the temperature Ta remains constant whatever may be the amount of heat transferred to the surrounding or transferred from the fluid to the object. Okay, here I am considering Ti is the initial temperature of the body and Ti is greater than the fluid temperature surrounding the body. Okay, at time 0, when I just quench the material or I just insert the material into the fluid, at that time period I'll consider time as 0, and at that time period the temperature of the body will be Ti, that is the initial temperature of the body, and the amount of heat transferred out of the body is given by H into A into T tau minus Ta, where T tau is the temperature of the body at any given time period tau. Now I will apply the energy balance equation here. So when I apply the energy balance here, the amount of heat transferred out of the body in time interval d tau. So this time interval is very much necessary. I am analyzing or applying the energy balance equation for a small duration of time, that is equal to change in internal energy of the body in the same time interval d tau. So the amount of energy transferred out of the body is given by that is the convective energy, H into A into T tau minus Ta into d tau, that is happening over a short duration of time d tau, and that should be equal to the change in internal energy which is given by mCp into dt. Here I'm adding a negative sign because I know Ti is larger than Ta and the body is losing heat, so the body is giving away heat. So there will be reduction in the internal energy. So I'm calling it I'm using a negative sign here. And the mass can be written as the product of density into volume. So I'm writing that as minus rho CpV into dt. And as I said, the TA is constant, whatever may be the amount of heat absorbed by it or heat emitted by heat given away by the fluid, the temperature of the fluid remains constant. So TA is a constant. Because of that, I can write dt as d of t tau minus Ta. Here dt is nothing but dt tau. Okay, because the differentiation of TA is equal to 0, so that is not going to change anything when we apply or when we use this term. Now I will rearrange this equation. As minus HA divided by rho CpV into T tau minus Ta into d tau is equal to d of T tau minus Ta. And then I will rearrange this. Now I will segregate the temperature terms on one side and the time term on the other side. So I can write the equation as d of T tau minus Ta divided by T tau minus Ta is equal to minus HA divided by rho CpV into d tau. Now I will integrate this between the limits. So I am applying the limit with respect to time, that is from time 0 to any given time tau. The temperature varies from T equals Ti to T equals T tau. At any given time, as I said, the temperature I call it as T tau. So when I integrate this, I'll get ln of T tau minus Ta divided by Ti minus Ta is equal to minus h into A divided by rho CpV into tau. I can take the ln to the other side. So if I do that, then I'll get T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus Ha divided by rho CpV into tau. Now what I'll do is T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus Ha divided by rho CpV into tau. Now what I'll do is I'll take this term, I'll take rho CpV divided by H into A and I'll call it as T. T is the thermal time constant. So here I'm using small t as thermal time constant. That's why I'm representing time by the term tau. Okay. When I replace this entire thing, that is rho CpV divided by H into A by time constant t, I'll get T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus tau by t. So this equation gives us the temperature distribution within the solid body as a function of time. So here you can see that this expression has only time as a parameter. There is no x, y or z in this equations. So we don't have x, y, z or any other spatial coordinates. We have only time coordinate. So this kind of this simplifies our calculation, and it also signifies that within the body there is no changes in temperature with respect to the spatial coordinates. Now let us see a few other important equations in the case of transient conduction. One is instantaneous heat transfer rate, and that is given by that is the amount of heat transfer which is occurring at any given moment of time. That is given by change in internal energy at that particular moment of time, that is mCp into dt tau divided by d tau, or it can be easily calculated with the formula h into A into T tau minus Ta, and the unit is watt. Then the total heat transfer is the total amount of energy transport from time 0 to any given time tau. So that can be calculated as the change in internal energy from initial time to any given time, that is mcp into t tau minus ti, which is also equal to integration of the instantaneous heat transfer rate over a short duration of time d tau. So the unit of this will be joules, and the maximum heat transfer is given by mcp into ti minus ta, that is the initial temperature of the object minus the temperature of the fluid multiplied by mcp will give us the maximum amount of energy transfer, and the unit is also joules. Now you can pause the video for a few minutes and you can note down the entire derivation. Now let us see the observations from this equations. So first of all, instead of writing t tau minus ta divided by ti minus ta every time, what I will do is I will denote t tau minus ta as theta and ti minus ta as theta I. So the equation can be written as theta by theta I is equal to e to the power of minus tau by t. That simplifies our writing. Now the first observation is the temperature distribution is exponential. So here the temperature distribution is a function of E. So the temperature distribution will be exponential. Initially at the initial stages or initial part of the heating or cooling, there will be a drastic changes in the temperature, but as the time proceeds, there will be gradual changes in the temperature. That is the exponential heating or the exponential cooling of the objects. That is the first observation. Then the second observation is with the help of this equation, either we can find out the temperature after attaining a certain duration of time, or we can find out the time required to reach a particular temperature. Then the third observation is that the time constant t is given by rho cp v divided by h into a. If the value of t increases for a given case, then which means here in this graph you can see that we have plotted graph for different values of t for the same condition, and to reach a particular temperature at a given temperature, so the y-axis represents the temperature or the ratio of temperature and the x-axis represents the time. So to reach a particular ratio here, if the value of t increases, then the time required to reach that ratio or that temperature also increases. So that is the third observation. And then the fourth observation is that the time required for a body to attain 36.8% of the applied temperature difference, that is Ti minus Ta, 36.8% of this, we call that time period as one time period, and this is very important in the case of thermo. In the next lecture, we will talk about the criteria on which we decide whether a given system can be